Hi students, I am Professor Awais Ahmed Hussaini, working as Assistant Professor in Mechanical Engineering Department at Sharad Institute of Technology, College of Engineering, Yadra. Students, in this video we will discuss some new simple numericals related with the second law of thermodynamics, that is based on that refrigerator, air conditioning, heat pumps. So as we know that the second law of the thermodynamics states that it is impossible to construct an device like refrigerator, air conditioner or heat pump working in a cyclic process whose sole purpose is to transfer the all amount of heat from lower temperature reservoir to higher temperature reservoir without add-on of external work. Means the meaning is for satisfactory operation of that device like refrigerator, heat pump or air conditioner, we must have to provide that work input to that device, that is for compressor. Then and then only it is possible to produce and work which is equivalent with that heat supplied minus heat rejected, that is Q1 minus Q2. And most important thing in case of that refrigerator and heat pump is the performance of that refrigerator or heat pump or air conditioner is calculated by calculation of the COP, that is coefficient of performance. That in case of the refrigerator, the coefficient of performance is equal to refrigerant effect upon work input to that device. Similarly, in case of the heat pump, the coefficient of performance is calculated by COP of heat pump is equal to heat gain, means whatever the heat input we gain upon work input to that device, that is heating effect upon work input to that heat pump. So these are some important basic fundamental things related with the refrigerator, air conditioner and heat pump. And main difference between refrigerator and heat pump is the refrigerator are mostly used to keep the temperature below the surrounding atmosphere in closed cabinet. Also in case of the in case of the heat pump, we can increase the temperature as compared with the surrounding. So in case of the heating purpose we use that heat pump, and for cooling purpose generally we use that air conditioner as well as refrigerator for closed contained space. Okay, so let us start with the first numerical. A domestic food freezer maintains a temperature of minus 15 degrees Celsius. The ambient air is at 30 degrees centigrade. Means the evaporative temperature is around minus 15 degrees centigrade. That is lowest temperature, and as compared with that the ambient temperature is around 30 degrees Celsius. So the lowest temperature is minus 15 degrees Celsius and the highest temperature is, that is surrounding, that is ambient temperature is around 30 degrees Celsius. If the heat leaks into the freezer at a continuous rate of, that is amount of heat supplied, that is QS, is around 1.75, you can say it as Q2 as well. So we have to find the power necessary. So what is the least power to pump the heat out continuously? So we have to calculate the least power, that is W. So these are some important given entities. So the first is that lowest temperature is given, it is around minus 15 degrees Celsius. We just convert it into Kelvin by adding 273, you will get at this answer. Similar way, the highest temperature is given, just convert it into Kelvin by adding 273. And important parameter, that is QS, is given. In other terms it is Q2. So this is around 1.75, and we have to calculate the work input to that particular device for satisfactory operation, that is W we have to calculate. So as we know that the Carnot COP is calculated by, there are two types of COP. The first is theoretical COP and second one is that Carnot COP. Also actual COP is there. Okay, so in order to calculate that Carnot COP on the basis of the temperature, the formula is the lowest temperature upon highest temperature minus lowest temperature. So the lowest temperature is given, that is 258, it is already given. Okay, and the highest temperature is also available with us, that is 303 Kelvin, and after putting that all values we will get that Carnot COP. So the Carnot COP is around 5.73. Okay, so in order to calculate that actual COP, the formula of the actual COP is, the actual COP is nothing but refrigerant effect upon work input to that device. So refrigerant effect is supposed to be that QS, and the value of the QS is already available with us. Okay, so by comparing these two, Carnot COP is equal to actual COP. The Carnot COP is already available with us. So here we already calculate that particular term of Carnot COP. Then by putting the values of the actual COP, that is QS, the QS is already known, that is 1.75. it is given in the numerical here. Okay, and the work input, that is unknown parameter, we have to calculate, and after that at the end we will get that work input, means least power necessary to pump the heat out continuously. Its value is around 0.305 kilowatt. So this is a simple numerical. Here you will get idea about how to find out the Carnot COP, actual COP, and work required to pump the heat out continuously. So students, keep in mind that in case of the refrigeration, air conditioning and heat pump, you must convert that temperature into Kelvin first. Then basically you must have to know the basically two formula. The first is that Carnot COP, and Carnot COP is calculated on the basis of the temperature. So the formula of the Carnot COP is lowest temperature upon difference of highest temperature and lowest temperature. So by putting values you will get the Carnot COP, and keep in mind that there is no any kind of the unit of the COP. Okay, and the next is that actual COP. Actual COP is calculated on the basis of the performance. The definition, as far as the definition of that actual COP, the actual COP is nothing but refrigerant effect upon work input to that device in case of the refrigerator, or in case of the heat pump, heating effect upon work input to that particular device. So in this way we can solve the simple numericals related with the refrigerator, heat pump and air conditioner. Now we will discuss the second numerical. A refrigerator works on the reversed Carnot cycle. So here I just noted that particular thing, reversed Carnot cycle, and it requires 0.5 kilowatt. So that 0.5 kilowatt is nothing but the work input to that device, okay, for satisfactory operation. So 0.5 kilowatt per hour is the amount of energy required for that machine of cooling to maintain a temperature of minus 15 degree Celsius. So that is lowest temperature here we achieve in case of the refrigeration system, that is around minus 15 degree Celsius. We have to calculate the three important terms, that is first is COP of the refrigerator, that is the first. They are not mentioned whether they want that actual or that Carnot COP, but on the basis of the given data it is very easy to calculate that actual COP as well. So we can use that formula of actual COP while calculating the first parameter. And second one is that the temperature at which the heat is rejected, we have to calculate, and amount of the heat rejected to the surrounding per kilowatt of the cooling. Okay, so in case of there is one refrigerator which produce temperature around minus 15 degrees Celsius, and for achieving that minus 15 degrees Celsius we must have to provide that 0.5 kilowatt per hour work input to that particular device, and we have to calculate that COP of the refrigerator as well as the temperature at which heat is rejected and amount of heat rejected to the surrounding per kilowatt of the cooling. So the given terms are that W1 work input is already given, that is 0.5 kilowatt per hour. Similar way that Q2 is already given. Here they mention per kilowatt, so that Q2 is nothing but 1 kilowatt. We can take that one as that particular value of the Q2, because here they mention the per kilowatt. Then the next is that T2, the refrigerator temperature is around minus 15 degrees Celsius. I just converted it into Kelvin by adding that 273. Now first I will calculate the first parameter, that is COP of the refrigerator. The COP of the refrigerator is calculated by using two formulae. The first is that Carnot COP and second one is that actual COP. On the basis of that given data, here we can calculate actual COP easily. So actual COP is equal to refrigerant effect upon work input to that device. So refrigerant effect in terms of the kilowatt is already given in the numerical, so that is 1 kilowatt. So I just put that value of 1 kilowatt here, and work input is half, already mentioned. So here we get the actual COP and its value is around 2. Now the second important is we have to calculate the temperature at which the heat is rejected. Means we have to calculate the value of the T1. The value of the T2 is already given with us. They are already mentioned. Now in order to calculate the temperature at which the heat is rejected, that is T1, again we are apply the formula of the Carnot COP here. Because if two temperature are come under picture, then we can use that formula of that Carnot COP. So Carnot COP is nothing but T2 upon T1 minus T2. Okay, so here that it is nothing but simply lowest temperature, that is you can write that TL, right? TL, that is lowest temperature, upon what? Highest temperature, that is T1, that is highest temperature. Okay, and minus what? Lowest temperature, that is TL again. Okay, so this is nothing but that particular formula of the Carnot COP. Okay, so the Carnot COP is nothing but lowest temperature upon highest temperature minus lowest temperature. The COP is already known, that is 2. We already calculated here, and the that lowest temperature is already given in the numerical, that is 257. Here it is, and T1 is unknown, minus that after putting the value of the T2, and after some mathematical calculation we will get the value of the T2. This is around 387. So this is the highest temperature. Okay, this is highest temperature T1. Here we get the second value, that is temperature at which the heat is rejected. Okay, so the now third parameter is amount of heat rejected to the surrounding per kilowatt of the cooling. Now in order to calculate that third parameter, that is amount of heat rejected to the surrounding per kilowatt of the cooling, that is Q1, we know the formula of that Carnot COP. On the basis of that Carnot COP, in terms of the heat, that is Q1 and Q2 is, that is heat supplied and heat rejected is, on the basis of temperature the Carnot COP is calculated by this. Okay, and on the basis of that heat supplied or heat rejected, the Carnot COP is calculated by using this method. So here I just reshuffle that temperature by that Q, that is amount of the heat, whether it may be rejected or that accepted or absorbed. So I just change the parameter, that is Q2 upon Q1 minus Q2. So Carnot COP is already known, then Q2 value is already known. Here we already, it is already mentioned in the numerical. Q1 we have to calculate, and Q2 is given in the numerical, and after putting all values in the standard formula and after some mathematical calculation, you will get the value of the Q1. It is around 1.05 kilowatt. So this is amount of the heat rejected to the surrounding. So in this way we calculate the COP of the refrigerator. Here we calculate the actual COP. In second term we calculate that temperature at which heat is rejected with the help of that Carnot COP, and third case amount of the heat rejected to the surrounding per kilowatt of the cooling. Also we can use the formula of the Carnot COP on the basis of the heat, and we get the answer. So students, in this way we can solve the simple numericals related with the heat pump, refrigerator and air conditioning. Now third very interesting question, that is operating temperature of the cold storage is minus 2 degrees Celsius. Means here the T2 is given, that is minus 2 degrees Celsius. I just converted into Kelvin by adding 273. Also at the same time the surrounding temperature is 40 degrees Celsius. So value of the T1 is given here. I just convert it into again Kelvin by adding 273. So this particular value of T2 here is this is a T2. Okay, or you can say it as the lowest temperature. Okay, so this is the lowest temperature, and this is the 40 is nothing but what? Highest temperature. You can write it as that TH. Okay, now into the cold chamber is around 30 kilowatt. Means the power required is around 30 kilowatt. If the actual COP of the plant is 1/10 of the maximum COP. So here they given. Okay, the relation is given, that is actual COP is equal to 1/10 times the maximum COP. What will be the power required? We have to calculate the power required to maintain the cold storage temperature at -2 degree Celsius. So these are the some options: 1.90 kilowatt, 3.70 kilowatt, 20.28 kilowatt, and fourth one is 46.50 kilowatt. So here they mention that 30 kilowatt as at Q value of the Q2, that is Q2. Okay, and finally we have to calculate that power required. So the correct answer is 46.50 kilowatt. How it comes we will discuss here. So once again I just give the introduction of that given parameters. The cold storage maintained, that is lowest temperature is -2, highest temperature is 40 degree. Then that heat means the refrigerant effect is generated around that 30 kilowatt, and actual COP is 1/10 of the maximum COP, and we have to calculate the power to reach up to -2 degree Celsius. So here I just draw the diagram as per the law of the Clausius statement. So here -2, that is T2, lowest temperature, 40 is the highest temperature. I just convert both temperature into Kelvin first, and that heat leaks, that is Q2 is around 30 kilowatt. Okay, the value of the Q2 is given, and we have to calculate that work, that is W in. Okay, so first we can start means according to this particular diagram, the Clausius statement, it is impossible to construct a device like a refrigerator, air conditioner or heat pump working in a cyclic process whose sole purpose is to transfer the all amount of heat from the lower temperature reservoir to higher temperature reservoir without add-on of external work. So for satisfactory operation of that cold storage or refrigerator plant to reach up to -2 degree Celsius, we must have to provide that W in. So we have to calculate that W in this case. So we know that the maximum COP, that is maximum COP is simply nothing but the Carnot COP. Okay, so Carnot COP is calculated by that lowest temperature upon a difference of highest temperature minus lowest temperature, and by putting that all values we get the maximum COP, that is Carnot COP. So Carnot COP is around 6.45. Here we get the answer. Now by using the relation actual COP, it is already given in the numerical. So actual COP is equal to 1/10 times of the theoretical COP. So 1/10 as it is, and I just put the value of that maximum, that is Carnot COP, that is 6.45, and we get the answer around 0.645. So this is what, this is actual COP we get. Now we know that the QL is already given, the Q2 is already given in the numerical, that is heat leaks. Okay, to maintain the -2 degree Celsius, it is already given in the numerical. Okay, so now we can apply the actual formula of actual COP. So actual COP is nothing but what? Actual COP is nothing but refrigerant effect upon work input to that device. So here actual COP we know, that is 0.645. Then that particular value of the Q2 is already known, it is given in the numerical, it is around 30 kilowatt, and by putting all values and substitution or by simple calculation we get the answer, it is around 46.50. So this is work input required to reach up to -2 degree Celsius. It is around 46.50 kilowatt. So students, in this way we can solve the simple numericals related with the refrigerator, heat pump and air conditioner. We just know the basic formula of Carnot COP, then actual COP while calculating simple numerical. Thank you. Our next video will be on we will take a few more numericals in order to get the good idea about that numericals related with the second law of the thermodynamics, that is refrigerator, heat pump and air conditioner. Thank you.